This is the first video lecture of 2 covering the material in Chapter 6. Chapter 6, like Chapter 5, studies probability distributions. But in this chapter, we're going to talk about probability distributions for continuous random variables. In particular, we're going to cover 2 different probability distributions in this chapter. In this short video, we're going to talk about the uniform probability distribution. And then, in the next video lecture, which is going to be a little bit longer than this video lecture, we're going to look at the normal probability distribution. When we look at the normal probability distribution, we will look at both the standard normal probability distribution and any generic normal probability distribution, and we'll learn about a link between the two that will allow us to calculate probabilities for any normal probability distribution using the standard normal. But for this video lecture, we're going to concentrate on this distribution right here, the uniform distribution. It's used not nearly as often as the normal distribution or the binomial distribution, but the uniform distribution is a nice place to start because it's simple. So it's a good pedagogical tool, and I'll use it at least 1, maybe 2 more times throughout the semester, and really as a pedagogical tool to teach you about things like sampling, distributions of the mean, etc. So we're going to talk about the uniform distribution and learn some very general things about continuous probability distributions in this video lecture. So continuous probability distributions, just in general, a continuous random variable is a random variable that can assume any value in an interval on the real line or some collection of intervals. I have given you that definition of a continuous random variable before, and we talked about random variables such as a person's height or weight. Other random variables that are continuous could be the mileage that your automobile gets on the highway. Other examples of continuous random variables could be economic indicators such as a person's income or their level of education. It is not possible to talk about the probability of a random variable that's continuous as taking on a particular value. Instead, what we talk about is the probability that the random variable takes on a value between 2 values. We can make these 2 values as close together, however, as we desire. Here's an example that will make these issues clearer. A random variable is uniformly distributed whenever the probability is proportional to the interval's length. The uniform probability density function is described with an equation. F of x in our previous chapter on discrete random variables stood for the probability function. To distinguish a probability function for a discrete random variable from the same type of a function, what we call a probability density function for a continuous random variable, we continue to use f of x as the probability density function, but we call it a density function rather than just a probability function. The word density basically tells us that what we're dealing with here is a continuous random variable. So our probability density function for a continuous random variable, f of x, gives us the probability, or we can use it to calculate the probability, that x takes on a value within some interval of possible values of the random variable x. The probability, f of x, for a uniform distribution is very intuitive. Since it's a uniform distribution, it will be the same for any fixed interval for the random variable x that includes values of x which are possible. In other words, values of x which are in between a and b. If you're looking at a value of x that's outside of the possible values for the continuous random variable x, then clearly the probability will fall to 0. So when we graph the probability density function for a uniformly distributed random variable, it's obviously going to look like a rectangle, which is exactly what makes this probability distribution so easy to study and learn from, is that basically calculating the areas of a rectangle is something that's very simple. So again, A is the smallest value that the variable can assume, and B is the largest value that a variable can assume. And when we graph the probability density function for our random variable x, as I said, it looks like a rectangle. And the base of the rectangle is equal to b minus a, and the height of the rectangle is equal to 1 over b minus a. This actually should not surprise you, since we know that the area under the probability density function should be equal to 1. That's according to our rules for assigning probability. Therefore, it must be the case that if we take the height of the rectangle, which is 1 over b minus a, and we multiply it by the base, which is b minus a, we should come up with 1, or 100% of the area is under the probability density function. So we can interpret right away the area under the probability density function as being, or the area under the density function as being a measure of probability. This is true not just for the uniform distribution, but it's true for any continuous distribution that might describe a continuous random variable. So just to give you a really simple example, it's intuitive, I think, to you that you know, the mean of the variable is right in between a and b. In fact, if we take, you know, sort of b minus a and we add that to a, right? So b minus a, and we divide it by 2 and we add that to a, we're going to end up at this mean here. We'll call it, probably should call it mu, not x bar. But we'll call that mu right here. And it should be obvious to you that with this distribution, 50% of the area is here, and the other 50% of the area is here. That means we have a 50% probability of drawing a value of the random variable which is greater than the mean, and a 50% chance of drawing a value that's less than the mean. And of course here, because the distribution is symmetric, right? I mean, it's not bell-shaped, but it's symmetric, the mean and the median are the same, so it's the same thing as saying that it's a 50% chance of drawing a value that's greater than mu and a 50% chance of drawing a value that's less than mu. So clearly these areas represent probabilities, and we can slice and dice up the intervals between a and b and easily calculate probabilities that a random variable x takes on values within those areas that are defined by our slicing and dicing of the horizontal axis here, which describes the value of x. So the uniform probability distribution, I'm going to give you an example that will make all of that much clearer. Let's say we're looking at Slater's buffet. Slater customers, they're charged for an amount of salad that they take at the buffet. So we're going to sample, and when we sample, it suggests that the amount of salad that's taken is uniformly distributed, and salad weights tend to be between 5 ounces and 15 ounces. So we don't observe any salads that have a weight that's less than 5 ounces, and likewise we don't ever observe a salad that is over 15 ounces. And we have a uniform distribution, so that, for example, the probability of somebody building a salad that's between, say, 5 and 7 ounces is exactly the same as the probability that they build a salad that's between 8 and 10 ounces, right? Since the interval there in both cases is 2 ounces, so a uniform distribution. In this case, the uniform density function, of course, is going to be equal, again, we know, to 1 over b minus a. That's from the previous slide. So our value of b is 15, and our value of a is 5. So 15 minus 5 is 10. So the probability density function is 1/10 if we're on the x-axis between 5 and 15, those are the possible values, the range of values that our continuous random variable can take on, and otherwise it's going to be equal to 0. Right? So here, our continuous uniformly distributed random variable is salad plate filling weight, which rhymes, which is very cool. Okay, so here's a graph then of our probability density function for our random variable x, and you can see that we have a lower value, an upper value of 15. 15 minus 5 again is equal to 10, so there's a 1/10 probability, or a PDF that's equal to 1/10. So in this example, just to go back to what we had talked about before, if you wanted to know the probability of a salad filling weight being less than 10 ounces, which is clearly the mean here, then we would take a 10th, right, multiplied by the difference between 10 and 5, 10 minus 5. Right, that would obviously give us this area here to the left of 10, and it should be clear to you that, the answer there is equal to 50%. The 50% chance, 0.5, 50% chance of getting a value that's less than 10. You could do this really for any two values that you choose. If you were to have 12 here, and you want to know the probability of getting a salad filling weight that was between 12 and 15, you would simply take 15 minus 12, right? That would be 3, and then you would take that 3 and you would divide it by the 10, 3/10, or a 30% probability of getting a salad filling weight between 12 and 15. So that's how you interpret the areas as probabilities. Something that's very general that we'll see again in other probability distributions that are more complicated. Okay, so very quickly we can also talk about the mean or the expected value of our uniformly distributed random variable x, and that's quite easy to calculate. It's a plus b over 2. Okay. And we could talk about the variance. The variance isn't quite as intuitive, but we're not going to derive the formula for the variance here, but given the formula for the variance that we have uncovered previously, we could take that and express it in continuous time with an integral. And actually, if you know a little integral calculus, this is an extremely easy formula to derive. But that's beyond the scope of this course. We don't use calculus in the statistics course. So with these types of formulas for variance for continuous random variables, you kind of have to take my word for it. I'd be more than happy to show you that if it's something you're interested in, but that would have to be outside of regular coursework. But we take b minus a, we square it and divide it by 12, and that gives us the variance of our uniformly distributed random variable. So in the case of salad filling weight, just to illustrate both of these formulas, we can calculate the expected value of x, the expected salad filling weight. We already know that's equal to 10, but you can verify that this formula works. 5 plus 15 is 20 divided by 2 is a mean of 10. And we can also apply the formula for a variance. The variance here is 15, that's the value of b, is 15, minus 5, the lower end of the range. We square that and divide it by 12, we get an answer of 8.3. Now remember that 8.3 is not measured in ounces, as our variable x is. We need to take the square root in order to get the standard deviation. If we want to measure that dispersion in terms of ounces, the same units of measure that we're measuring the mean in. So you take the square root of 8.3, I think it's around 2.8, and you get a standard deviation there of 2.8. So the standard deviation would be somewhere around 2.8 ounces in our distribution.